There it is. All right. So for posterity's sake, this is the Math 114 Exam 1 review in the spring semester of 2024. Recording that for the video since sometimes these get reused. In fact, I think the old fall review is currently on D2L right now. But I said I wasn't going to do much more ado, and then there I go again. So anyway, practice exam. Let's do this thing. So if you're on D2L, you can find the written version of these class notes of this review by going to the class notes, clicking to the exam review tab on the left, and then practice exam 1 should be the first entry since it's exam 1. Yep, cool. Let's move. Let's move on. So the cover page of the exam looks pretty similar to this one. You'll be given the formula S equals R theta. That one's given right there. In addition to that one, the very last page of the exam is going to contain all of the identities. So the cofunction identities, the Pythagorean identities, and the reciprocal identities. I'm not asking for those to be memorized on exam 1, so I'm just going to give them to you. Again, it's on the very last page. So if you'd like to tear that page off the back so that you can have it on other pages, that's totally fine. If you do remove the formula sheet on the back page, you do not need to turn it back into us. You can just hang on to that. We don't need extra loose paper floating around, so it's yours to keep if you rip it off. Or it'll be yours to keep when you get it back in a week. Because these things come back to you. But okay. The first question on the exam, the first page of the exam, is exactly this page right here. It's a blank copy of the unit circle, and we are going to ask you to just fill some of it in. Specifically, we're going to be asking for all of the points and the angles in radian measure. If I come highlight some of this stuff, we want angles in exact radian measure, and also we want the exact X and Y coordinate point. So what we mean by that is, let's just do one example. This first angle is pi over 6 radians, so you should include that. And it's at the XY point, square root of 3 over 2, comma 1/2. And you'll just fill this out for each of the 16 angles on the unit circle. Another one on here, don't forget 0, which is at 1, 0. Or 2 pi, which is at 1, 0. Probably just put 0 there rather than 2 pi, but I think you'll get points either way. Yeah, so just do that for all of them. You do not need to include degree measure, but you can if you want to. So that's a 30-degree angle, but we're going to be grading specifically on the radian measures. So make sure you put the radians on each angle. And again, this is the exact format that you'll see on the exam. Or at least the one that's on paper. All right, up next, I had to make a slight correction to the practice exam because it gave us some information that was going to be not valid. So I had to change that to just say, instead of whatever used to be there, I don't even remember anymore. It's now that tangent of theta is less than 0 and the sine of theta is 1/9. And we're going to use trigonometric identities only. So we're going to solve this one without a reference triangle. Look at reference triangles again later to find the exact value of cosine of theta. So let's go do that. Shapes. Give me a one of these. Yeah. Hey, look, a coordinate plane. So if I use what I know about positive and negative signs for sine, cosine, and tangent, I can place my angle theta in one of the 4 quadrants. Namely, if I look at the fact that tangent of theta is less than 0, I know that I have to be either in quadrant 2 or in quadrant 4. Right? Tangent being negative is going to follow a negative slope. So from your perspective, it's that way. So quadrant 2 and quadrant 4 are the 2 quadrants where tangent is negative. If I move that on to sine of theta, I know specifically sine of theta is equal to 1/9, which is a positive number. So if sine of theta is positive, I'm either in the first quadrant or in the second quadrant. And since those two bits of information overlap in the second quadrant, that must be the quadrant that theta is located in. So my solution should be in quadrant 2, which means when I go to get the cosine value, I should have a negative answer. I'm just going to put that in the box right now. I know that cosine needs to come out negative because my angle's in the second quadrant. And now let's do a bunch of work to figure out what the number for cosine is. So I need an identity that relates sine of theta to cosine of theta. They are taking the same input angles, same theta is getting plugged into both sine and cosine, which means I don't want a cofunction identity, even though that kind of relates sine and cosine together. But I have to switch the angle in order to do that. Don't want to switch my angle this time, I want to keep the same one. So if I want to relate sine theta and cosine theta together, I should instead use a Pythagorean identity. Namely, cosine squared plus sine squared is equal to 1. But if I rearrange that for cosine squared, just subtract sine squared over to the other side, I get cosine squared is equal to 1 minus sine squared. And again, they have the same input angle theta. Which tends to be important once we start mixing in multiple angles in one problem. But we know all of that, so let's just plug some stuff in. This is 1 minus 1/9 squared. I can start simplifying that expression to be 1 minus 1 over 81. But now I'm going to be subtracting a fraction from a number. So I want to rewrite 1 also as a fraction. Call that 81 over 81. Since 81 over 81 would reduce back to 1. But now that subtraction's pretty straightforward. 81 minus 1 is 80. All of that over 81. So 80 over 81. Make myself a little bit more space here. All right, since that's what my expression is gonna, what my expression would simplify. Now I want to get just cosine of theta, which means I'll need to take a square root of both sides. The square roots of 80 over 81 I'll simplify in a moment. But because I'm taking the square root of cosine squared, I should have a plus or minus show up. I've mentioned it once or twice before, but I'll say it again here. Anytime we take the square root of a variable, we should have a plus or minus show up. Plus or minuses aren't always necessary if I'm taking the square root of a number, but they are if I'm taking the square root of a variable. In this case, cosine theta, because it's got a theta in it, is going to be considered a variable. So that thing's a variable, a plus or minus should show up, but we talked about this at the beginning of the problem. I want to choose the negative answer out of that plus or minus, because I'm in the second quadrant where my x values are negative, which means my cosine value is negative. So this thing is equal to negative square root of 80 over 81. Let's simplify that a bit. The denominator is already a square number. So that one's easy. Square root of 81 is 9. Up in the numerator, I want to rewrite 80 as a product of a square number and non-square numbers. So probably something like 16 times 5, which is equal to 80, but notably 16 is a square number. So I could pull that to the outside of my square root and get 4 root 5 over 9. And this answer is still negative. Make sure that that's there. So the answer that goes in the box, 4 root 5 over 9. So let's talk about exam answers. If you had given me negative square root of 80 over 81, you just wrote that in the box. Especially on a 3-point problem, that's going to be worth full points, right? So you could write down this answer right here. You got, okay, cosine theta, blah, blah, plus or minus. It's got the square root on there. Pick the negative value, square root of 80 over 81. That'll be fine enough. That's if it's a free response question. If this is a multiple choice question, meaning I'm giving you a bunch of answers to choose from, the answer that I'll be putting in the matching box is this negative 4 root 5 over 9. So you've got to be able to at least get down to this answer for a multiple choice question. But if you left it unsimplified in a free response section, unless we specifically say reduce all of your, simplify your answer as much as possible, leaving it like square root 80 over 9 or something, we'll still get points for that. Okay. All right, the number 3, dealing with some angles that aren't exactly on the unit circle, but are very close to something that's on the unit circle. I mean, at least reminiscent of that. So like negative 4 pi over 3 and 17 pi over 6 both have denominators that are familiar from the unit circle. Anything that's a something pi over 3 or a something pi over 6, I can relate that back to the unit circle, but I might need to do some work to get there. So these answers are coterminal to other angles that are on the unit circle. We just need to figure out which angles they're coterminal to. So the important idea here is that a coterminal angle is one that is different by exactly one circle, or exactly some whole number multiple of circles. So if I add or subtract 2 pi from any angle, get a coterminal angle. And those have the same exact values for sine, cosine, tangent, etc. So if I wanted to find the cotangent of negative 4 pi over 3, and I hold my pen the right way, I'll take negative 4 pi over 3, and I'm going to add 2 pi to that number. It's currently a negative angle. I want to get it back to a positive angle, hopefully one that I recognize from the unit circle. So I'll add 2 pi, which is the same as 6 pi over 3. Right? 2 pi, 6 pi over 3, same number. It's just that 6 pi over 3 has a common denominator with the angle I'm interested in, which makes my math easier. So 2 pi over 3, negative 4 pi over 3 and 2 pi over 3 are coterminal. So I want to find the cotangent of 2 pi over 3, because that's something I'll know from the unit circle. Then cotangent values, you probably don't have those memorized, but hopefully you have the tangent values memorized. So I'll rewrite this thing as 1 over the tangent of 2 pi over 3, which is 1 over negative square root 3. And then I'll rationalize that number. So multiply by root 3 over root 3, root 3 over root 3. Why don't we actually put that in another color? And then that simplifies to negative square root of 3 over 3. Hi there. Why is it negative? So we are in the second quadrant where 2 pi over 3 is located. And in the second quadrant, tangent values are negative. It's only sine values that are positive in quadrant 2. On to the next one. I've got 17 pi over 6. This time it's larger than the unit circle, so I should subtract 2 pi to get 5 pi over 6. say that those two angles are coterminal. Before I get too far ahead, the question on Zoom. For this problem, I did cotangent is cosine over sine and and solved that way. And that is also a perfectly valid solution. If you did that, you should have gotten the same answer I did at -√3/3, or at least -1/√3. So yeah, you could solve it either way, either as the reciprocal of tangent or as cosine over sine. Gotcha. So I have the tangent values off the unit circle memorized. So I know that tangent of 2π/3 is √3. So all of my tangent values, tangent of π/6 is √3/3. Tangent of π/3 is just √3. Tangent of π/4 is 1. So I'm using that knowledge. Go through a shortcut here. If you forget the tangent values, then fall back on sine and cosine. So I could have instead done cosine 2π/3 over sine 2π/3, and then just grab those values. Circle. All right. Back to problem 2. We just found that 17π/6 is coterminal to 5π/6, which means that they both have the same value for sine. And the sine of 5π/6 is +1/2. Also, we know that is from the unit circle. No extra work required there. And finally, the cosecant of 7π/4. That one's already on the unit circle, so we don't need a coterminal angle this time. We just need the reciprocal identity. The cosecant is equal to the reciprocal of sine. The 1/sine of 7π/4, which is 1/(-√2/2), which is -2 divided by √2. I will rationalize that thing to get -2√2/2, which simplifies one last time to just -√2. Those twos reduce one another. So cosecant 7π/4 is -√2 again. Hold that there for just a moment. So I moved a little fast through some of that work. Take a question. Where does the 7π go when you simplify? So the 7π, so the 7π is just the numerator of our angle. So that 7π/4, which is our angle, stays inside of the trig function. And our trig function, which was cosecant, is now going to move to the denominator to become 1/sine of theta. So that same entire angle still gets plugged into sine. So I'm still taking the sine of 7π/4. Hopefully that answers the question I was just looking at. Let me know if you were asking something different. But I think that's what it was. Hi.
So the sine 7π/4 using the calculator.
Sure.
Like
Exactly. So when I'm going from sine of 7π/4 to -√2/2, I'm just using the unit circle to do that.
just look over the cycle that side. 7π/4.
It'll be in the fourth quadrant. So down here. Yep, and it's the π/4 angle down there. Yeah, and keep in mind that the first page of the exam is the unit circle. So you could always flip back to that page to check your answers after you filled it out right at the beginning of the exam. And then the second question.
We need to memorize the tangent, like how
Oh, the tangent value?
yeah, like
So the question was, do you need to memorize the tangent values on the unit circle? Strictly speaking, no, because if you have sine and cosine memorized, you could just derive the tangent values at runtime. I think it's easier if you have them memorized, but it's not necessary because you could just always say, you know, tangent's sine over cosine, and you know both of those two numbers, so you can just generate the number on the fly on the exam. But problems tend to move a little smoother if you do have them memorized. And so I'll take this moment to remind everyone that all of the exams are in recitation. And with the current structure of the course, or at least the one that's happening in spring of 2024, some recitations are online and some are in person. So go to your recitation like you normally would on Thursday or tomorrow or today, whatever time you're listening to this recording, and take the quiz or take the exam in recitation. If you have recitation in person, you take it in person. If you have recitation over Zoom, then you'll take it over Zoom. Really meant to be directing that more down here. Yeah. Okay, moving on. Here's a triangle. Given this right triangle here, find the exact value of the following identity and then use some fancy math to figure out what's going on. So step one, complete the identity secant of 90 degrees minus alpha. Well, that's cosecant of alpha. Oop, bring that back over here. All right, that's just one of our cofunction identities. The cofunction of secant is cosecant. And it is saying that the cosecant of 90 minus alpha is equal to cosecant of alpha. And to complete this diagram, 90 degrees minus alpha is this red angle in the lower right corner of the triangle, while alpha itself is the blue angle in the upper left. So when we're looking to solve the secant of 90 degrees minus alpha, that would be the hypotenuse over, the hypotenuse over the side adjacent to the red angle, 90 minus alpha, or it's equal to the cosecant of alpha, the cosecant of the blue angle, which is equal to the hypotenuse, still 11, over the side opposite the blue angle, both of which happen to be that lower side, which I'm going to call y. So you got to call it something and use the Pythagorean theorem to solve for it. And yes, you will be given a list of identities on the exam. They'll be on the very last page of the exam. So let's go to that Pythagorean theorem. I have a couple of sides that I know already. I know my hypotenuse is 11. I know that my left leg is the square root of 57. So I'll say root 57. Well, let's try that again. Root 57 squared plus y squared is equal to 11 squared. And solve that thing for y. So this ought to look like y squared is equal to 121. So that's 11 squared minus 57. Do that arithmetic real quick. 121 minus 57 is 64. And finally, I can take a square root here and get that y is the square root of 64, or 8. Now, this triangle is just a triangle out in space. It's just a triangle that exists. It's not in the coordinate plane. This is not a reference triangle. So I don't need to consider negative sides on this triangle. Again, not in the coordinate plane. It's just a triangle. So all side lengths will be positive on this guy. So just positive 8 for y. So in the end, I need to come up with an answer for this secant or cosecant value. Either way I do it, it should be 11 over y, or 11 over 8. If I go with cosecant of alpha, cosecant of the blue angle, I want the hypotenuse, which is 11, over the side opposite that blue angle, which is 8. Right, and then let's knock out a multiple choice section, similar to stuff that you'll see on the part 1 of the D2L exam. So given a few things, figure out where some stuff is. So I've got a negative cotangent value and a positive secant value. Let's take a look at these two things. Secant follows cosine, because it's just 1 over cosine. So this thing is positive in quadrant 1 and quadrant 4. If I look back at the cotangent value, it's negative. Cotangent will be following tangent. Wherever tangent is negative, cotangent is also negative, which will be in quadrants 2 and 4. Then I just need the quadrant where those two things overlap, which is quadrant 4. Let me actually write that a little bit more cleanly. Quadrant 4. There we go. Next up, an angle in standard position that measures -8 radians is in which of the following quadrants? There are only 4 options, 4 of them. It's not going to be no quadrant. I guess it could be if we were exactly equal to one of the borders between quadrants, but that's not the case here. Notice specifically that this is -8 radians and not -8 pi radians. Because there is, in fact, a difference. So what I want to do is convert -8 to a coterminal angle that's on the unit circle somewhere. So between 0 and 2 pi. I'll do that by adding 2 pi to 8. 2 pi is just a little bit over 6. I'll still have a negative number if I add 2 pi only once. So I'm going to add 2 pi twice to get back to a positive coterminal angle. Twice 2 pi is about 12, so that'll definitely end up positive. Plug that into a computer or a calculator. Computers are calculators. I got 4.56. And then just compare 4.56 to the boundaries between quadrants. Pi is 3.14, and 4.56 is bigger than that. But 3 pi over 2 is 4.71. So again, this is, stop. This is pi, this is 3 pi over 2. If I'm in between the pair of those angles, I must be in quadrant 3. So quadrant 3 for this one. And yes, the exam, part 1 of the exam, the one that's all on D2L for everybody, that one's just multiple choice. Very similar to the way that all of the quizzes have been multiple choice on D2L. And the in recitation exam is going to be all free response. So this section is much more similar to part 1 of the exam. Right, number 7, let's find a pair of coterminal angles for -7 pi over 15. There are an infinite number of choices for this one, but I'll just find the 2 coterminal angles that are closest to -7 pi over 15. One of those is -7 pi over 15 plus 2 pi, or plus 30 pi over 15. gets me to 23 pi over 15. The other closest coterminal angle to negative 7 pi over 15 is the one that goes backwards instead of forwards. So minus 2 pi or minus 30 pi over 15, which looks like negative 37 pi over 15. So I'll look for a multiple choice answer that contains those two. And fortunately, it's still on screen. Option E. Those two. Ooh, bunch of questions in chat. Ah, cool. Looks like it took care of itself. All right, and next up, let's calculate a reference angle for 37 pi over 30. If we take a quick look at 37 over 30, it is between 1 and 1.5. 1 to 37 over 30 to 1.5. So as a fraction of pi, this coefficient, 37 over 30, more than 1, less than 1.5. That means that 37 pi over 30 is in between pi and 3 pi over 2. So we're in the third quadrant. 1, 2, 3. And in the third quadrant, quadrant 3, let's mark that again. Our reference angle is theta minus pi. Which I get to be 37 pi over 30 minus 30 pi over 30. Let's get ourselves a common denominator. My result is 7 pi over 30. You'll know you've got a valid answer if you get a solution that's in the first quadrant. 7 over 30 is smaller than a half. So 7 pi over 30 is smaller than pi over 2. Right? 1/2 would have been 15 pi over 30. 7 is smaller than 15. So we're in the first quadrant. I feel like that's a good answer. Let's go circle A. 7 pi over 30. Questions do we have? Thanks. All right, pick up the pace a little bit. So we've got a couple of word problems up ahead of us. First one, given that the radius of the Earth is approximately 3,960 miles, find the distance between Dallas, Texas, and Omaha, Nebraska. But real quick, back to the previous question, how I know to find specific reference angles, right? I don't know, how do I know which angles are in which quadrant? Gotcha. So if I'm trying to establish an angle in a specific quadrant, I need to compare the angle that I'm working with to the 4 quadrant boundaries. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. I just need to slot my angle in between 2 of those. Whichever 2 it fits between is the quadrant it has to be located in. So really that means I'm looking at the coefficient on pi. So in the problem that we just did, 37 over 30, I could just plug that into a calculator if I wanted to. It's going to be about 1.25. Pretty close to it, maybe close to 1.2. But either way, 1.2 or 1.25 fits in between 1 and 1.5. Because it's in between 1 and 1.5, it's got to be in the third quadrant. Because it's in between 1 pi and 1.5 pi. Yeah. 30 pi over 30 just is pi. But it's pi with a common denominator. Nice. Yeah. All right. Back to here. Given the radius of the Earth is try again. Given that the radius of the Earth is approximately 3,960 miles. Find the distance between Dallas and Omaha. Dallas and Omaha just happen to be due north and south of each other. Omaha being the one that's further north, because Nebraska is north of Texas. Here's a couple of latitudes that those things are located at. Figure out the distance between them. Now, since these cities are pretty far apart, we're going to need to take the curvature of the Earth into effect when calculating their distance, which means we're going to want to calculate an arc length rather than just a flat distance between them. So if I draw in my equator, say that this is 0 degrees, say this is 0 degrees, because that's where the equator is. I have two cities, Omaha, which is kind of further north, and Dallas, which is kind of further south. I'm going to exaggerate my angles so that it works. So it's a little bit easier to read. The center of the Earth is about right there. If I connect those two cities, draw the radius that connects to the center of the Earth, I can form an arc with an angle that subtends it. The arc, this purple distance between Omaha and Dallas up there, and I have some angle that formed with the center of the Earth between these two cities. And that angle right there, the angle that's between the two cities, or the latitude difference between the two cities, is just the difference in their latitudes. Kind of gave that one away. But so theta should be 41.26 minus 32.79. I got 8.47. So lastly, I need to get my arc length here. So S equals R theta, where it is particularly important that my angle be measured in radians. Formula won't work if it's in degrees. So I've got to convert that 8.47 degrees into radians. This is 3,960 times 8.47 times pi over 180. Right, that conversion factor at the end will put me into radians instead of degrees. And from there, I can just plug it into a calculator. When I did that, I got 585.40, and that'll be in miles. Because in the end, my answer should be a distance. My angle is just the thing that's in radians. Right, and then up next, we have a medical alert helicopter flying at a given height. Helicopter emergency crew sees an ambulance at an angle of depression of 62 degrees. Find the distance of the ambulance from a point on the ground directly below the helicopter. So let's do that. We've got a helicopter. Well, not my worst helicopter. Yeah, cool. Helicopter, it's flying up in the air. It is above the ground. So I should draw the ground in. How about right there? It's flying up at a height or an altitude of 734 feet. So I'll draw my altitude in, and it's going to spot an ambulance on the ground somewhere. And it'll spot it at an angle of depression of 62 degrees away. Yeah, that's right. That's going to be a really steep angle. Now, let me just not draw this to scale. I'll exaggerate my angles for for effect. So the ambulance is on the ground over here, and I'll connect my 2 points. Okay, cool. Here we are. I know that this height is 734 feet. I know that I'm looking to find this distance x down here. And I want to solve that thing from there, making sure that I label my angle of depression. So remember that both angles of elevation and depression always need to be measured from a horizontal line. So I need to draw one more piece into my diagram. Being a horizontal line right at the helicopter, and then label my angle of depression as this guy right there. AOD. Be careful that you don't label it as the angle that's on the inside of the triangle that you drew in, because that angle should be 28 degrees rather than 62. Make sure your angle of depression is labeled on the outside. It connects up to a horizontal line, and that, you know, angles of elevation and depression aren't connected to vertical lines. We don't want to do that. That'll mess it up. But that means we could start solving for stuff inside this triangle. If I'm working inside of the triangle, I have an angle of 28 degrees instead of 62. Its opposite side is x, its adjacent side is 734. So I should set up a tangent equation. So tangent of 28 degrees is equal to x over 734. And solve that thing for x. Just need to multiply 734 to the other side. I'll also just rewrite it so x is on the left. X is 734, which means that the 3 comes before the 4. 734, there we are. Tangent of 28 degrees. Just plug that into a calculator, and you should hopefully get 390.27. Make sure you're in degree mode on this one, because we needed to plug a degree angle into a tangent function. So that mode on your calculator is always going to matter when we're plugging stuff into trig functions. All right, to get this next one, determining whether the point -1 over 5, 4 over 5, the point that is on the terminal side of an angle theta in standard position, is that point on the unit circle? To check that, we should write down the equation of the unit circle, which is x squared plus y squared equals 1. Unit circle just is a circle centered at the origin with a radius of 1. So we just go to the equation for a circle centered at 0, 0 with a radius of 1. That's the equation for our unit circle. Plug our point in and see what happens. If we get 1, it's on the unit circle. If we don't get 1, it's not on the unit circle. So this thing should look like -1/5 squared plus 4/5 squared, which is 1 over 25 plus 16 over 25, which in turn is 17 over 25. I'm not always very good with numbers, but I'm pretty sure that that is not equal to 1. If it were equal to 1, it would have been 25 over 25. And we didn't get that. We got 17 over 25. So since x squared plus y squared was not equal to 1, this point is not on the unit circle. Next one down is going to ask us to find the exact value of secant theta. And I'm going to say, because I'm running low on time, you should use a reference triangle to find it. reference triangle. One note that I do want to make here is that secant is not equal to -5. Secant of theta is not -5. Secant theta is not -5. Just like cosine of theta is not equal to -1/5. Even though the x value of our point is -1/5. Cosine itself won't be -1/5 here. The identity that we're using there, that cosine is the x value, sine is the y value, that kind of stuff. Those equations only work if our point is on the unit circle. We saw previously, point wasn't on the unit circle, so our identities for x equals cosine theta, y equals sine theta don't work in this case. So we'll need a reference triangle to solve it instead, and I'll save that for later. This thing will be posted to D2L after it finishes compiling, which will take it a little bit after I end the recording. So hopefully by like 3 o'clock. And we are out of time for class. So if you've got somewhere else to be, feel free to take off and go do that. If you'd like to stick around, I've got about 10 minutes before the next class comes in. I'm going to finish as much of this as I can, and then I'll record some other stuff later. But if you do want to stick around, like I said, I'm just going to keep going with the next couple problems. As I can. Get to at least one more question before I have to cede the classroom. So let's go as fast as we can, but not too fast. Okay, so given the stuff we see before us, secant is equal to -37/35, and sine of theta is negative. So secant's negative and sine's negative. That means I'm in quadrant 3. Secant being negative means x is negative. Sine being negative means y is negative. Both x and y negative must be the third quadrant. And yes, we're gonna look at how to tell if a negative is required when filling out our reference triangles right now. So secant is hypotenuse over adjacent. I just saw that this triangle should be in the third quadrant. So we are gonna draw it in the third quadrant when my assist is gonna help me better than that. I'll put my coordinate axes in right there and label a few things in here. This theta right here is my reference angle. It's the one that's inside of the triangle. The actual angle theta itself in standard position is this angle right there. And since I know secant is hypotenuse over adjacent, I should have a 37 for my hypotenuse and a 35 for my adjacent side with a missing value y. Now, I'm in the third quadrant, so both x and y should be negative. So I should have a negative on this 35, and I'm also going to have a negative on y once I solve for it. So go to the Pythagorean theorem to figure out what y should be. I'll have something like -35 squared plus y squared is equal to 37 squared. Solve that thing for y squared. If you go to your calculator, 37 squared minus 35 squared will leave you with 144. That's a calculator bit. Don't expect you to do that, in your head or by hand. Then I can take a square root of both sides. Square root of 144 is 12. And because we're in the third quadrant, I want -12. I'll get a plus or minus there, and I'm going to choose the negative value. So over here, y is -12. From there, I know everything that's in my reference triangle. I'm going to use that to solve for a few other trig functions. We aren't looking at even identities just yet. So a more accurate quiz question would be just find the cosine of theta. I can get that from my reference triangle. adjacent over hypotenuse is negative 35 over 37. Negative 35 over 37. After that, I'm looking at the cosine of pi over 2 minus theta. I can use one of my trig identities that I know I've got on the last page of the exam to find sine of theta. And go back up to my reference triangle. I want opposite over hypotenuse. So negative 12 over 37. So negative 12 over 37. And lastly, on this problem, I want tangent squared. Tangents opposite over hypotenuse. So negative 12 over negative 35. That whole thing squared. I got 144 divided by 1,225. 144 over 1225. And on to the final problem, which again, I'm going to go through right here before the next class starts, hopefully. I can get it done in 2 minutes. So I want to solve this trig identity. So first thing I want to notice, I have 40-degree angles and 50-degree angles, both present in the problem. Now, I want to make sure that I only have one angle in the problem when I'm verifying one of these identities. So I want to switch around some of my angles so that I only have either 40 degrees or only 50 degrees. I have fewer 50-degree angles, so I'm going to change those around first. So if I just rewrite those two pieces, tangent squared of 50 degrees will go to cotangent squared of 40 degrees. Plus 3 fraction. That's sine of 50 degrees. Through a cofunction identity, I'm going to set that to cosine of 40 degrees. Right, now that I've rewritten those two 50-degree angles as 40-degree angles instead, I'm going to leave the rest of my problem alone. So this is still 8 minus 3 cotangent of 40 degrees minus 2 times cosecant squared of 40 degrees. And this sine of 40 degrees in the denominator over there, I'll also leave that the same. So my first step every time I verify one of these identities is always apply cofunction identities first, get just a single angle in the whole problem. After that, if I have any square trig functions, I'm probably going to want to use a Pythagorean identity. So this bit right here, cosecant squared of 40 degrees minus cotangent squared of 40 degrees, is a quick rewrite of one of the Pythagorean identities. That whole thing is equal to 1. So normally we have 1 plus cotangent squared is equal to cosecant squared. But if we rearrange that problem slightly, we'll see that 1 is equal to cosecant squared minus cotangent squared. I'm also going to use an identity on the right side, cosine 40 over sine 40. That's just cotangent of 40 degrees. Since cosine over sine is cotangent. Leaving the other pieces alone, 8 minus 3 cotangent 40 degrees. I have a positive 3 cotangent 40 degrees and a negative 3 cotangent to 40 degrees. Those two pieces together ought to add to 0. So we're looking at, in my new line, 8 plus 0 minus 2. Right, 2 times 1 will just be 2. Kind of keep that thing going over here. 8 plus 0 minus 2 is 6. So in the end, my answer to the whole thing is just 6. Again, to quickly review that problem as a whole, 3 sort of big steps. Cofunction identities are always first. Change the problem around to have only a single angle in it. Second, deal with any Pythagorean identities you have. You'll know you have one if there's a square trig function. And finally, use either reciprocal identities or change everything to sine and cosine for your final simplification step. Cool. And that's there. Hi, question. Gotcha. So this is an older practice exam when we were still doing even and odd identities on exam 1. We aren't doing that right now, so don't worry about negative angles. Yep. So just start from the first line that I had written down. Yeah. Cool. All right. I'm gonna start ending things there because I know the next class wants this classroom. So good luck on the exam on Thursday or whenever it is when you're listening to this recording. And I'm gonna stop it there.